Hey, you've got Dr. B here, and let's review the first module here. The topics include the scientific method, SI units, sig figs, mass and density, energy, and heat capacity. What I'll do is I'll read each question and I'll provide the answer. If you really want to learn this stuff, I suggest you pause it and try to answer it on your own and see how you did. What's an observation? Well, it's something you see. Technically, that would be, whoops. An observation can simply be made by looking through the eye or through instrumentation. I think that's a good point because with the instrumentation, you can see beyond the visible wavelengths. What's a hypothesis? Most people say an educated guess, but what they say is a statement or question based on an observation. You see the sky is blue and you wonder why. Interesting that they point out it could be in the form of a question. A hypothesis. I wonder why the sky is blue. Was an experiment. Well, that sounds like something you would design based on your observation. So it's a procedure to test the validity of a hypothesis. Sounds good. What's a theory? I usually say that's an answer based on a lot of information, right? And what they say, it's an in-depth and full explanation of an observation based on theory and laws. It's surprising they don't say it's based on experiment. I would add that as well. What's a law? And I would say that's an answer that can never be changed. They would say it's a law, it's a concise statement based on observation, theories, and experiments. Surprising they don't really say anything about the permanence of a law or the attempt to make a law permanent. What's a control? That's a standard for comparison. And if it's a placebo, that deals with a negative control, right? Like a starch pill for an experiment to deal with, say, a pill for the common cold. It's something that's supposed to do nothing to make sure that the patient thinks it does nothing because they don't always act that way. Okay, SI units and conversions. Let's convert from numbers to scientific notation for starters. This one's scientific notation. It looks like it's 23800. Notice there's no decimal place. That would have made it 4 or 5 significant figures, but we want only 3. For when it's less than 0, count from the decimal place to a number between 1 and 10. I'd draw a line there. So 0.002384 is equal to 2.384 times 10 to the minus 3. I'll try to read the question in case you're just listening to this podcast style. We have 6.02 times 10 to the third meters. Convert that to kilometers. Well, there's 1,000 meters in a kilometer, so it sounds like we have much fewer kilometers, maybe 6.02, right? But mathematically, start with what you're given, 6.02 times 10 to the meters, draw 10 to the third meters, draw a line. There's 1,000 meters in a kilometer. Make sure your meters cancels. Don't draw upside down. Do the math, and you get 6.02 kilometers, 3 sig figs. We have 3.6488 times 10 to the minus 8 inches. I would like that in centimeters. You can look up any conversions you want. The one that I remember is that 2.54 centimeters is an inch. Therefore, we're going to have more, right? More centimeters than inches by a factor of 2.54. It's almost tripling it. So we get 9.2680 times 10 to the minus 8 centimeters. Do not mess with the number of significant figures. Okay, you know what? Actually, for this one, I think we should. See how I think there's an error here. And I'll fix it later, but see how there's 3 sig figs here and much more there? We can only report this to 3 sig figs. The best answer is 9.27 times 10 to the 8th minus 8th centimeters. Okay, 6.42 times 10 to the minus 4th miles for every 4.42 hours. Just punch it in and your units will be miles per hour, which is 1.45 times 10 to the minus 4 miles per hour. If you're going at 29 meters per second, how many miles per hour is? Well, that's going to require 2 conversion factors that you could look up. I would say 1609 meters is a mile and 3600 seconds is an hour. Set it all up as a nice clean unit conversion. There's my meters per second, and notice that I'm converting from meters to mile. Meters over meters equals 1, and seconds to hours. Seconds over seconds equals 1. So that cancels, final units, meters per hour. Final answer, 65 miles per hour. Note 2 sig figs. This is what limits it right there. 63.4 milliliters to cubic centimeters. Start with what you're given, well, or recognize that they're interchangeable. It's one of those weird things in science. It's the same thing. Typically, they're using cubic centimeters for solids and milliliters for liquids, but they're interchangeable. Bada bing. 28 Fahrenheit to Kelvin. I just looked it up. There is a formula for it. It's annoying. That's 270 Kelvin. A little bit warmer. You know what? That can't be. Oh, yeah, that is right. 28 Fahrenheit is cold. 200 Celsius, 270 Kelvin, where 273 Kelvin is freezing. I'm a little bit under that. Notice that I'm ballparking to make sure my answers are right. It's always a good idea. How many sig figs in 0.002384? There's no units there. That's fine. Well, we can always dump those leading zeros, so I get 4. 6.0238 times 10 to the third meters. How many significant figures? We do have a unit, but it doesn't ask you for it. It just asks you for a number. Central zeros are always significant, so all 5 are significant. Let's convert from 3.6488 times 10 to the minus 8th inches to meters. I know that there's 39.37 inches in a meter. Punching that in, we get 9.2680 times 10 to the minus 10th meters. I'm going to once again say that we really need to modify this answer. I'm going to say this is an error. We need to change it. The raw number's fine, but since there's only 4 sig figs here, I'm going to change this to 9.268. I'd drop the 0. We should only have 4 significant figures in our answer. 3.4 plus 6.126, all divided by 3.66435, where the top number's in parentheses. Okay, there's a lot here, and there's several of these. I kind of really like these now that I understand them pretty well. Step 1, you really got to do your Pemdas. That means do things in order. Anything in parentheses will go first. We'll write down the raw number for that, but we'll draw a line after the 10th value, because since we're adding, it's only going to be accurate to the 10th. That will mean for the subsequent conversion, since it's accurate to the 10th. Interesting. It's accurate to the 10th. Yeah, it is accurate to the 10th, but I think this will mean you have 3 sig figs. Let's see how this rolls. It's just under 10. It's 3.4 plus the 6.126 is equal to 9.526. Draw a line under the 5, meaning for the next operation, since that was accurate to 10th, this number has 2 sig figs, but we carry along all the details, and we divide it by the 3.66435. We get a big honkin' raw number. 2 sig figs here on the top, ton on the bottom. We'll keep 2 sig figs. The answer is 2.6 with no units. Try it again for this one. These are the harder questions, so notice what we do is we get a raw number with a line under it indicating significant figures, and we'll need that for the final calculation. Now, in this case, everything's getting multiplied, so, I mean, just turn that into a whole raw number, divide 17.4 divided by it, and keep 3 sig figs, it looks like. So here's the raw number when we do the bottom part, of which there's plenty of precision there. I mean, there is going to be only 4 sig figs, but this one only has 3, so we'll keep 3 sig figs. The answer is 0.648. Try this one, and this would get mastery if you can get this. I'd really recommend you pause this, because these ones are probably the harder or hardest questions you might see. All right, so we'll get a raw number for this, 2.55 minus 0.7. We'll underline it at the 10th place, meaning it has 2 sig figs. We'll take that whole thing, multiply it by the 4.3002, write down the whole enchilada, but recognize that it's only good to 2 sig figs, 7.95, round up, and we get 8.0. All right, let's solve for density. Density is mass over volume. I drew this little triangle here, which some people like, some people hate, but it shows you how to relate all of these. This means multiply, that means divide. This looks like direct plug-in. Grams over milliliters is density. Plugging in and keeping 2 significant figures, we get 0.69 grams per mil. For this one, we've got a volume and we've got a mass. I'd say this is also direct plug-in. And the units are kilograms per cubic centimeter. Since this only has one sig fig, we have to report this to one sig fig. So you might have gotten like 138, something like that, but you got to round it to only one number, and there it is. Solving for mass here, we've got a density and we've got a volume. I like to use this. Look, mass equals density times volume. So just punch them in. Now the units cancel nicely for milliliters. Keep 2 sig figs, 1.4 times 10 to the fourth grams. Volume equals mass divided by density. Therefore, punch those in. There's your mass. There's your density. Grams divided by grams cancels. 1 over mils equals mils. We get 3.7 mLs. That 17 limits it to 2 sig figs. Is it endo or is it exo? Going uphill is always endo. That means like melting something or boiling it. You're applying heat underneath it. So that means it's endothermic. Anything going the other way must be exo. It takes heat to melt ice. Endothermic. Steam condensing is going downhill. It's not boiling, it's condensing, therefore exothermic. Blood is freezing. It's not requiring that heat to melt your frozen blood. It's releasing it, and so when you freeze something, it releases some energy. That sounds odd, right? Because it's getting colder. But energy and temperature are two different things. Let me move my little image here. I hope that shows up. Hardest question. We got 362 joules of heat that are applied to some water at 36 degrees. How hot will it get, assuming no heat loss? Well, it's going to get hotter than 36 degrees, and it's not given, but it really should have been, that the specific heat of water is 4.184 joules per gram degrees Celsius. That means every time you add 4.184 joules, it's going to go up a degree. So that will make it hotter by a lot, right? Because 362 divided by 4.184 is a lot. But that's for each gram. It's for 5 grams, so it will be 1/5 of that. That's the logic, but you're better off very much doing this in terms of starting with what you're given. I'd start with 4.184 joules per gram degrees Celsius, but since the answer is going to be in Celsius, that's temperature, and 4.184 joules per gram degree Celsius has Celsius on the bottom, I'd flip it over. Otherwise, you're going to end up with a 1 over Celsius. That can't be right. So check it out. I put 4.184 joules is required to heat 1 gram, 1 degree Celsius. They are equivalent, but the Celsius on top, which makes me happy, because when we multiply it by those 362 joules, the joules cancel. That's good. And we are dividing 362 by 4.184 like we knew we would. We're also dividing it by 5 because it's for each gram, and we've got 5. That will make it go up less. Punching it all in, we get grams is canceling, joules is canceling. The only unit left standing is Celsius, so it must be perfect. It's going to go up by 17.3 degrees Celsius. Oops, that's not what they asked. They said the highest temperature it will reach. It started at 36. It got 17.3 higher. The answer is 53. Since this number is only accurate to the whole number, we're not going to say 53.3. We're only going to round it to the nearest whole number. That's the rule for adding numbers. And the final answer is 53 degrees Celsius. If all that made sense, I'll bet you're going to do really well on the Module 1 quiz.